Today we're going to be solving 3 questions that I chose from paper 1 of the AA standard level exam from this year, May of 2024. And we're going to start with questions 1 and question 6 because I found it very interesting that they started and finished section A with the same content, which was sequences. So they had an arithmetic sequence in question 1, then a bunch of other stuff in the other questions, and a geometric sequence in question 6. Now, because question 6 wraps up section A with the short questions, and then the next question is already in section B, it's not necessarily the case that question 7 will be more difficult than question 6. It's just longer, has more parts, A, B, C. But in terms of looking out for difficult questions where you don't necessarily spend too much of your time, question 6 is definitely supposed to be a difficult one, and also question 9, of course, the last one of the paper. But I found it very interesting that they started and ended on sequences because a lot of times my students ask me, what are the most difficult topics in the syllabus to look out for? And I always like to answer that there is no such thing as an easy topic or a difficult topic. What does exist are easy questions and difficult questions, but those can be done in any topic. And I found it so pretty that this paper decided to exemplify that with a very easy question about sequences and then a very difficult question also about sequences in the same paper. So let's go through that. Question 1, you have U2 and U4 with a difference of 12 between them. So you went through 2 terms, right? There is U3 in the middle. So of course the common difference needs to be 6. And then to find UN, well, he says more words. It's like find an expression for the general term UN or something like that. But you're just going to apply the formula, which is to put the first term. Oh, we don't have U1 yet, but U1 is 4 because it's 10 minus 6. So you put the 4 and then you add the n minus 1 times the common difference 6, and then you're done. You can expand that if you want. I don't think it's necessary. I didn't put part B of the question 6 here yet just because it didn't fit on the board, okay? But let's do part A and then we'll move on to part B. Because question A is actually kind of easy. It's just worth 1 mark, I think. Yes, 1 mark. So you have U1, you have R, you want to find Sn. So what are you going to do? You just put it in the formula, right? So it's going to be U1 is 1, so I'm not even going to put it there. It's U1 times 10 to the power of n minus 1 divided by r minus 1, which in this case is 9. Okay, so here is part B. Already it doesn't start out very well because it is a show that question, and I am not a big fan of show that. But seriously, this is not why this question is difficult. It's difficult because it is asking us to add up a bunch of terms, and the terms are called S1, S2, S3, all the way until Sn. So this really looks like the sum of a sequence, which is something that we think we are familiar with. We have a formula for the sum of an arithmetic sequence, and we have a formula for the sum of a geometric sequence, which, by the way, we have just used in the previous item. So it looks familiar. We think we know where we stand. And we should definitely start by plugging in the result from part A into all of these terms here, S1, S2, S3. This is all I'm doing for now, okay? I'm plugging in 1, 2, 3 for n in this formula here. So that's why it's looking like 10 to the power of 1, 10 to the power of 2, and so on. Now, even if you don't do anything else in this question, I think it's still a good idea to do this because it looks like you're doing correct things and you might get a mark for it. But when we try to move on from here, it still looks like the sum of a sequence. It still looks familiar, but we only have formulas for the sum of 2 particular types of sequences. We know the sum of an arithmetic sequence, and we know the sum of a geometric sequence, but this thing is neither of those things. That's why it's difficult, because it kind of looks familiar, but not really. So you have to use a little bit of creativity in order to manipulate this expression into another way of looking at it that will make it even more familiar, so that then you can apply the formulas that you have for those very familiar situations. But whenever you are required to use creativity, that necessarily makes the question a little bit more difficult. So that's what's happening here. And I am going to try to simplify this expression as if I don't even know where I'm going, just trying to make it simpler because often this is a good thing to do. So the first thing that I want to do is to factor out a 1 over 9 here because all of these fractions are over 9. And I just think it will look simpler if I don't have a bunch of fractions. So things that are simpler to look at a lot of times are also more easy to understand. And I do see that this is not an arithmetic or a geometric sequence, but there is a geometric sequence in there if you skip a few terms. Because if you skip all the minus ones and you just look at the 10 to the power of things, then that is a geometric sequence because it's always multiplying by 10 in every term. So what I think I want to do now is to get those minus ones out of there. I'm going to move them more to the end of the sentence and all of the tens to the power of something's closer to me because I'm allowed to do that, right? This is just adding up a bunch of terms, so the order doesn't matter and I'm allowed to change the order. So that's what I've done now. And now I see a bunch of minus ones together. So if it's like minus 1, minus 1, minus 1, minus 1, just 4 of them, that is equal to negative 4, right? And so on. But the thing is that it's not 4. I don't know how many they are exactly, but I know that the amount is represented by the letter n, which is the index of the last term that I was adding there. So I kind of know how many ones there are. It's n ones. So that's a minus n right there. And this part here, now it's perfectly familiar. This is the sum of a geometric sequence with first term equal to 10. Well, 10 to the power of 1. I don't really need this 1 there. So the first term is 10 and the common ratio is also 10. So I'm just going to put the formula for geometric sequence here again and the minus n that came from that part. Now, once again, 10 minus 1 is 9. And you begin to see where this is going, right? Because 9 times 9 is 81, which is what's happening over there. And you still need the 9n over there. This n doesn't have a 9 in front of it. But you can just put it there by multiplying the n by 9 over 9, which is 1, which is really good because now you have both fractions in the same denominator. So the 9 is going to multiply that other 9 as well. It's going to be the 81 over there. Everything is finished. And the other question I also wanted to talk to you about was question 8. That's already in section B, but it's in the middle of section B because it has 7, 8, 9. So it's not supposed to be the easiest of section B, and it's not supposed to be the hardest either. It's supposed to be intermediate. And the thing that section B questions can also do is that they can vary the difficulty within the same question because they have multiple parts. And this question is definitely going to do that because part A is sketch the graph of this rational function for 5 marks. This could have easily been a question 2 just by itself, just do this. Because it's familiar, it's repetitive, you've probably done a lot of exercises that are exactly like this when studying for this test. So what do you do for those 5 marks? You correctly place a vertical asymptote, horizontal asymptote, x-intercept, y-intercept, and then you connect everything by sketching the graph correctly. And I have a whole video about that, which I am going to link in the description. But for now, let's just do this one. And I always like to start with the easiest things first. And I think that in this type of exercise, the easiest thing is the vertical asymptote because it's given, right? It's the point that is outside of the domain, and I didn't write it here, but the question did say that the domain is x different than 2, as it has to be, because if x was 2, then we would be dividing by 0, which we can't. So anyway, vertical asymptote, x equals 2. Please don't forget to label your asymptote with its equation. Don't just leave it hanging there with nothing, but also don't just write the number 2. The name of the asymptote is x equals 2. And then the next easiest thing that I think is the y-intercept, because y-intercept is f of 0. And in order to get that, I just pretend that x is 0. So 0, 0, 2 over -2 is -1. That's my y-intercept. I think I'm going to go for the horizontal asymptote now before I do the x-intercept. And the horizontal asymptote is what happens when x is very, very large. So if x is very large, 2 will be small. Like, it's not that the 2 changed in size. 2 is still 2. But when compared to something very big, then 2 becomes really, really small. And so does this 2 up here. So both of them become irrelevant. And for x very big, what we are seeing is f of x equals 4. That is our horizontal asymptote, y equals 4, which we also label. We don't forget to put the label in the graph. I know that I still haven't calculated the x-intercept, but now I already have enough information to sketch. So I'm going to sketch by connecting the dots right now. Please don't forget to include both sides of the function in your sketch. And now let's calculate the x-intercept, which is this number right here, by asking when is this equal to 0? There you have it. X is -½ which I've put in the picture there. Now, the next few items are not very interesting, so I'm just going to read and not actually do them. Write down the range of f for just 1 mark because it's a write down. The range is all real numbers except for 4 because it's the horizontal asymptote. And then he moves on to talk about a different function. He leaves that one there and asks about a function g, which is now a quadratic function. And he asks a bunch of things about the quadratic function, but in the end, because I want to get to the really interesting part of the question, in the end, you just know all of the things that I'm going to write down here about the function. And some of them you found out, some of them were given in the question, but you're going to use all of them anyway. Now comes the really interesting part. So you know all of these things about this quadratic function that you just got a few marks for learning. And you still have this other function, which is a rational function that you were working with before. And now to wrap up the question, he asks you for the number of solutions where you're setting one equal to the other. So you are asking for the number of intersections between the graph of this and this other graph here. Now, this is tricky. This is the last item in a section B question. It can be considered difficult, yes, because every time that you are asked about the number of solutions, you feel like this is familiar. You feel like this is going to be a question about the discriminant of a quadratic function, because you are talking about a quadratic function right here, so why not? The discriminant is b squared minus 4ac, and it talks about the number of solutions in a quadratic equation. So that's where you think this is going. You feel that it is familiar, but not really, because you are not in that universe. You are not talking about the number of solutions of a quadratic equation. You are talking about the number of solutions of this equation, which is not quadratic. It has this rational part here. And you could think of simplifying the situation here by multiplying both sides of the equation by x minus 2 to get rid of this denominator. And if you really are feeling like wasting some precious minutes during your exam by doing all of this distributive, you will come up with a polynomial of degree 3, but that's just not going to be useful in this question. Because here's the thing. Polynomial equations of degree 3, which this is, they do tend to have 3 solutions. So you could think, I'm going to do that. I'm going to say it's degree 3, so therefore it has 3 solutions. But it's not true that they always have 3 solutions. And by the way, even the fact that it has 3 solutions, that is high level content. You're not supposed to need that for a standard level exam. And even if you do that, you take the time to distribute and then you say, well, it's a polynomial of degree 3, therefore it has 3 solutions. You're still wrong, because not all polynomials of degree 3 have 3 solutions. So you're just saying that it does, but you are not justifying your conclusions. So no, that is not what this question is about. This question is about sketching. We are going to sketch this quadratic function. We know a lot of things about it, so we have options of where to start. I'm going to start by marking the zeros. It says so right here. The zeros are negative half and 9/2. Negative half was a coincidence because it was also one of the zeros of my other function, and 9/2 is right here. Now, as for the vertex, I think we're going to have a coincidence as well because the vertex is at coordinate x equals 2, which is also the vertical asymptote of the other function. So anyway, 2 and minus a lot, right? That's very big negative. It's like -6. So there you go. That's the vertex. So now let's just connect the dots and make it look like a quadratic function. And now we answer the question, how many intersection points does this have? Well, there's one here, and one here. So there's 3. I don't think you need to say anything else about it. I think this is enough. But if you wanted to argue some more as to, well, maybe there is a 4th one that we are not seeing in the window that we sketched, well, there isn't. Because on the left, the red function is never going to pass the horizontal asymptote, and the green one clearly has already passed it, so they're not going to meet again. And to the right here, after this intersection, the red function is always decreasing. It's decreasing towards its horizontal asymptote, and the green function is increasing, so they're not going to meet again. I was actually a little bit too careless here. I should have marked the y-intercept as well. We have that. It's -9/4, so it's a little below -2. This one's -1, so this one is definitely under it. And the reason why that could be important is because if the y-intercept of the green function was above that of the red function, then there was a chance that instead of crossing, they could actually touch here, just making one intersection and then a second one over here on the other side, making the final answer 2 instead of 3. But my sketch is not perfectly to scale, but it is kind of to scale, so I knew this was not going to happen with these numbers. I'm always very happy when I can find the answer to something kind of complicated just by looking at it like this. I am a very big fan of doing math with my eyes. I always like to sketch everything, even if the question doesn't necessarily ask me to. And I always try to convince people that sketching and looking at things with your eyes is a helpful mathematical tool. You're not doing less math because you're working with sketches than if you were manipulating something algebraic. No, this is not less math. This is more math. This is good math, and it's something that you should create the habit of doing. But usually when I solve a question in this kind of way, afterwards, there's always some sort of way that I realize, oh, this could have been done blindly without looking at it. And in this case, it's about the coincidence of the zero there, the fact that the negative half was a zero of both functions. You already knew that about f from part A when you found the x-intercept, and you know that about g as well because it's right here. One of the zeros is negative half. So you don't want to work with a polynomial of degree 3 in a standard level question. Definitely not. But what you can do is put your quadratic function into factored form. And then if you really want to see the x plus half on this side as well, you can factor out just a 4 from this function. You're looking for the number of intersections. So you keep in mind that x equals negative half is one of the intersections as you cancel out this factor from both sides. And now you are going to multiply both sides by x minus 2. Now this is a quadratic equation. You're going to have to distribute that to put the 4 on the other side, and then you're going to use a discriminant and figure out that this has 2 solutions. And putting it together with the third solution that you had just found, then that is 3 solutions. Be careful though to check that one of the 2 solutions that you're going to find here is not negative half, because then it would just be 2 solutions instead of 3 solutions. I don't like this way of solving this question. This kind of thing is when I feel I would have never thought of that. because what I think of is sketching. I want to look at what I'm doing. And if you want to see more examples of questions where this kind of thing happens, I have a whole other video about it. Those are not IB questions, but they are the same kind of thing. And I was happy to see this question in this paper because now I have a very nice example from an IB question for when I want to talk about doing math with your eyes.